Welcome back to the Deep Dive. We're continuing our journey through the OEIS, and today we're diving into a sequence that really caught my eye. It's A000161.
Ah, yes.
Now, it might seem simple at first glance, just about representing integers as the sum of two squares, but trust me, there's a whole lot more to uncover here. And to help us unpack all of this, we have a very special guest, a Fields Medal-winning mathematician. Welcome to the Deep Dive.
It's a pleasure to be here. I'm excited to delve into the sequence with you. It's one of those mathematical gems that seems simple on the surface, but quickly leads you down some fascinating rabbit holes.
Absolutely. So let's start with the basics. The OEIS defines A000161 as the number of partitions of n into two squares. Can you break that down for us a bit? What exactly do we mean by partition in this context?
Sure. Think of it like this. You have a certain number of blocks, say, and you want to arrange them into two squares. A partition is just a way of dividing those blocks up. So if you have like 5 blocks, you can form one square with 1 block and another with 4 blocks. That's one partition.
Oh, so it's not just about finding any two squares that add up to the number.
Right.
It's about the specific ways we can split the number into those two squares.
Exactly. And the sequence tells us how many different ways we can do that for each integer.
Okay, got it.
Yeah.
Now, looking at the first few terms of the sequence, we have 1, 1, 1, 0, 1, 1, 0, 0, 1. I noticed some zeros in there. What's the deal with those?
That's where things get really interesting. Those zeros represent the integers that simply can't be expressed as the sum of two squares, no matter how hard you try. For example, the number 3. You just can't find two squares that add up to it.
I see. Okay, so that makes sense. Now, there's a comment on the OEIS page that mentions a connection to similar sublattices of a square lattice. That sounds pretty abstract. Can you help us visualize what that means and how it relates to our sums of squares?
Absolutely. Imagine you have a regular grid, like a piece of graph paper. Now picture smaller grids within that main grid formed by picking specific points, and these are sublattices. It turns out that the number of ways to form these sublattices with certain properties is directly related to the numbers in our sequence, A000161.
Wow, so we're going from sums of squares to visual patterns on a grid. That's a surprising link. It's almost like these abstract numbers are suddenly taking on a geometric form. But how does that actually help us understand the sequence better?
Well, it gives us a way to see why certain numbers can't be represented as the sum of two squares.
Yeah.
Let me try and sketch out an example on this grid paper here. See how certain points just wouldn't fit into any possible sublattice no matter how you arrange them?
Right.
Those points represent the numbers that our sequence labels with a 0.
Okay, I think I'm starting to get it. It's like the lattice acts as a filter and only certain numbers can pass through.
Yeah, that's a great way to put it. The lattice provides a sort of visual framework for understanding those underlying constraints of representing numbers as sums of squares.
Interesting. Now, there's another comment mentioning different pk values, which I guess stand for partitions into k non-zero squares. Are these connected to our sequence A0000000161 in some way?
Definitely. The comment points us to some related sequences on the OEIS, like A010052, A025426, and so on. These sequences deal with partitions into, well, 1 square, 2 squares, 3, 4, and even up to 5 squares. You can think of A000161, which focuses on partitions into 2 squares as a specific case within this bigger family of sequences.
So it's like we're zooming in on one particular slice of this larger concept of partitions and sums of squares, and each sequence offers a different perspective on the idea.
Precisely. Each one gives us a slightly different lens through which to examine this really intricate world of number theory. It's like we're exploring a multifaceted gem with each facet revealing, a different sparkle.
I love that analogy. Now, the formula section is next. And there are a few different ways to calculate the terms in A000161 listed here. Can we break down these formulas a bit? I know formulas can seem kind of intimidating, but I have a feeling they hold some key insights.
Sure, let's start with the first one, which uses set notation. It might look a bit cryptic at first, but it's really just a formal way of saying what we've already been talking about, counting all the pairs of squares that add up to a specific number, n.
Okay, so it's just expressing the idea in sort of mathematical language. What about the second formula? It mentions something about divisors and modulo 4. Is that where things get a little more complex?
Well, it does introduce a new concept, modulo arithmetic. But before we jump into modulo 4, let me illustrate the basic idea with something simpler, like modulo 2. Think of dividing a number by 2. What are the possible remainders you could have?
Well, you could either have a remainder of 0, which means the number is even, or a remainder of 1, meaning it's odd.
Exactly. That's modulo 2 in action. Now, modulo 4 works similarly, only we're looking at remainders after dividing by 4. And the second formula for A00000161 is all about counting the divisors of a number that leaves specific remainders when divided by 4.
Interesting. So it's not just any divisor, it has to fit this specific modulo 4 condition.
Yeah.
I'm starting to see how these formulas add another layer of complexity to the problem.
They do. And they also highlight the interconnectedness of seemingly, different mathematical concepts. Who would have thought that remainders from division would have anything to do with counting sums of squares?
Right. It's amazing how these things connect. Now, I'm curious to see how these formulas actually work in practice. The OEIS page has an example for A25. Can we walk through that one?
Of course. The example shows that A25 equals 2, meaning there are two ways to represent 25 as the sum of two squares, and we can verify that. 3 Veneta plus 4 beta gives us 25, and so does 5 Monera.
Ah, I see. So one representation uses two different squares, and the other uses the same square twice, and both count towards our total. Okay, it's a nice clear illustration of how those formulas translate into actual ways of representing the number as a sum of squares.
Exactly. The formulas, even though they may seem a bit abstract, are directly reflecting this core principle of counting the distinct ways to represent a number as the sum of two squares.
Okay, I'm following you. The OEIS page also provides some code snippets in various programming languages. Why are those included? What's their relevance to understanding this sequence?
Well, those snippets, which are written in languages like Python, Haskell, they're practical tools for actually generating terms of the sequence. They can be incredibly helpful if you want to explore the sequence beyond those first few terms listed on the page. You can plug in any integer and see how many ways it can be expressed as the sum of two squares.
So it's a way for people to experiment with the sequence themselves and see how those formulas actually play out for larger numbers. That's super useful, especially if you're someone who's studying number theory.
It is. It bridges that gap between the theoretical concepts and the practical exploration, allowing really anyone with some basic programming knowledge to kind of dive in and discover patterns for themselves. And speaking of exploring further, let's take a look at the references section.
Okay, great. It lists a variety of books and research papers. What kind of information can we find in these references?
Well, they kind of showcase the breadth of areas where this seemingly simple sequence pops up. For example, there's a book by Ouspensky and Heazlitt on elementary number theory, which provides a good foundation for understanding many of the concepts we've touched on today. Then there are more specialized works, like Grosswald's book, which focuses specifically on representations of integers as sums of squares.
So these references provide a roadmap for anyone who wants to go deeper into this topic. They can see how A000161 fits into the bigger picture of number theory and how it connects to, all these other fascinating mathematical ideas.
Exactly. It's a reminder that even something as seemingly simple as, a sequence about sums of squares can have far-reaching implications and connections within the world of mathematics. And there's also that paper by Conway, Raines, and Sloane that you mentioned, the one on similar sublattices. That one really dives deep into those geometric connections we were talking about, with the grid. It really highlights how A000161 can be visualized through the structure of those lattices.
It's kind of amazing to think that we can go from sums of squares to these visual patterns and then even delve into more advanced concepts. It's like this one sequence is like a key that unlocks this whole network of mathematical ideas.
It really speaks to the elegance and the beauty of mathematics, how, these simple concepts can lead to such deep, profound insights and connections.
As we're looking at this OEIS page with all its comments and formulas and references, it really feels like a collaborative effort. It's like a whole community of mathematicians have contributed to our understanding of this sequence.
That's the spirit of the OEIS, yeah. It's a testament to the collective wisdom and the collaborative nature of mathematics. Mathematicians from all over the world sharing their discoveries and insights, building upon each other's work. It's a beautiful thing.
It is. From your perspective as a Fields medalist, what is it about a sequence like A000161 that captures the interest of mathematicians?
Yeah.
What sparks that curiosity in research?
Well, I think, for one, there's the element of surprise. You start with a seemingly straightforward question: how many ways can we represent a number as the sum of two squares? And all of a sudden, you're uncovering these links to lattices, modulo arithmetic, even deeper topics in number theory. It's like peeling back layers of an onion, each layer revealing something new and unexpected.
It's like a mathematical detective story.
Exactly. Each clue leading to a new discovery, a new insight. And there's also the aesthetic appeal. Mathematicians are drawn to patterns and symmetry, elegance, and this sequence exhibits those qualities in abundance. The way it connects seemingly disparate concepts into this harmonious whole is just, well, beautiful.
It's like we're discovering this hidden order within the universe of numbers.
And finally, I think there's the potential for application. While A00000161 might seem purely theoretical at first, its connections to these other areas of mathematics often lead to practical applications. In cryptography, for example, or computer science, even physics, you never know where these mathematical explorations might lead.
So it's not just beauty and elegance. It's also about that potential to unlock solutions to real-world problems. I'm also struck by, the historical aspect, this problem of representing numbers as sums of squares. It's been around for a while now, right?
Right. Oh, yeah, absolutely. The study of sums of squares goes all the way back to ancient Greece. Mathematicians like Diophantus were exploring these concepts centuries ago. And over time, giants like Fermat, Euler, and Gauss, they've all made huge contributions to our understanding.
It's amazing to think that we're part of this long lineage of mathematical inquiry, building on the work of those who came before us.
It is. It highlights the fact that mathematics is this constantly evolving field, with new discoveries and insights emerging from the foundations laid by, previous generations. We're all part of this ongoing conversation, this quest to understand the language of the universe.
Speaking of history, are there any particular stories or anecdotes about mathematicians and their work on sums of squares that come to mind?
Well, one that I always find fascinating is the story of Pierre de Fermat and his famous two-square theorem. He stated that a prime number can be expressed as the sum of two squares if and only if it leaves a remainder of 1 when divided by 4.
Oh, that sounds familiar. Is that connected to that modulo 4 concept we talked about earlier?
It certainly is. Fermat's work was, really foundational in our understanding of how divisibility and sums of squares are intertwined. And what's fascinating is that he stated this theorem without actually providing a proof. It took decades for other mathematicians to come up with a rigorous proof, and that journey of discovery is really a testament to that collaborative and challenging nature of mathematics.
Wow. So even a simple-sounding statement can lead to, decades of exploration and new insights. That's incredible.
It is, and it reminds us that even in a field as seemingly well-defined as mathematics, there's always more to uncover, more to explore, more to prove.
Yeah,
Okay?
for sure. It seems like this sequence, A000161, is almost like a microcosm of number theory itself. We've got the history, the patterns, the connections to other areas, the potential applications. It's all there.
You've hit the nail on the head. It's a beautiful example of how a single sequence can open a window into this vast and intricate world of numbers. And that's what makes the OEIS so special. It's a portal to countless mathematical journeys, each one waiting to be explored.
You've given us a lot to think about today. Before we wrap up our deep dive into A000161, is there anything else you'd like to highlight? Any final thoughts you want to share with our listeners?
Well, I just encourage everyone to appreciate the beauty and the depth that lie within these seemingly simple mathematical concepts. Don't be afraid to dig deeper, to explore those connections, to ask questions. Who knows what mathematical treasures you might uncover along the way?
Absolutely. It's been really eye-opening to dive into this world of sums of squares. And I'm sure our listeners will be, checking out those references, maybe even trying out some of that code to see what they can discover.
I hope so. And remember, the OEIS is constantly growing and evolving. New sequences are added all the time, new connections are made, new insights are emerging. It's really a testament to that boundless nature of mathematical exploration.
So even after our deep dive here, there's still so much more to learn and discover about A000161 and all those other sequences in the OEIS.
Precisely. Every sequence is like a starting point for a new adventure, a new opportunity to unravel those mysteries of numbers and their relationships. It's like having this infinite library of mathematical puzzles right at your fingertips.
Well said. This has been a truly fascinating exploration of A000161. Thank you so much for sharing your insights with us today.
The pleasure was all mine. I always enjoy, having the opportunity to talk about the beauty and the power of number theory, and I hope our listeners will continue to explore the OEIS and all the wonders that it holds.
And to our listeners, thanks for joining us on this deep dive into the fascinating world of OEIS sequence A000161. We hope you've gained a new appreciation for the depth and beauty hidden within this seemingly simple sequence.
Until next time, happy exploring.
Keep those mathematical minds engaged. We'll catch you on our next deep dive into the OEIS.